Hello everyone. This video is about binary classification on imbalanced dataset, which is a common situation you're going to meet when doing classification problems. We're going to introduce the idea and the techniques we use with an example of a company. Nowadays, predicting customers' purchasing behaviors has been the focus of marketing strategies. And with the rapid growth of recent digitalization, we now have access to numerous amount of data. But at the same time, you have to be smart enough to be able to use the data well and generate a good profit of a business. The background story is we are having a large chain of premium wine and chocolate store, and the store introduced a new chocolate product. And before spending substantial funds, the CEO wants to conduct an initial feasibility study. They sent the sample product for free to 40,000 target customers among their 2.5 million members and recorded whether the customer ordered the new product within 1 month or not. Based on the data, we aim to develop a customer targeting model to improve marketing efficiency and ultimately improve the profit gained by the new product. We know from the company that they are expecting a $35.5 profit from every customer that buys the product, and the cost of targeting one customer is $6.6. First, let's look at a data set. As mentioned before, we are having 40,000 data points and 21 attributes. Here is a description of the attributes. You can take a look. The dependent variables, the Y's of our dataset is the buyer flag, which is really easy to understand. 0 means not purchasing and 1 means purchasing. Second, we move on to data preprocessing. We remove ID and previous sample. These two attributes, by their definition, should be irrelevant to the dependent variable. And then we randomly divide the dataset into training set, validation set, and the test set with a ratio of 80, 10, and 10. Now let's talk about the choice of model. The first model that comes into our mind is logistic regression. The reason is because this is a binary classification problem, and sigmoid function generally works really well. And the second model we want to use is the support vector machine. This is an advanced classifier because it can provide non-linear decision boundaries with the use of a kernel. And let's see some first trial results. Here's the logistic regression. You can see the accuracy is around 91.45%. Oh, sorry. And the support vector machine with RBF kernel. Here the test error for this model is 8%, which means the accuracy on the test set is around 92%. So the accuracy seems to be really good, but there is a huge problem. If we look back to the results, we can see that the model is almost predicting no, and in SVM actually it is predicting no 1 values. So basically the model predicts every data point as 0. For a company, of course, you doesn't lose any money. You make no mistake if you doesn't take any action. You didn't target any customer, but at the same time you make no profit. Then why are you here? Why are you doing a business, right? So the problem is because we are having a skewed data set. If we look at a training set and test set, we can easily see that more than 90% of the data in the set are labeled as 0, and there's only less than 10% that are actually labeled as 1. As a result, every classification model we build will tend to predict much more zeros than ones. And let's think about a naive classifier. So the classifier doesn't know anything and just blindly predicting every data point as 0, it will still have a baseline accuracy around 92%. So based on this discovery, we can see that accuracy is not a good evaluation of our model here. So we have to look at other measurements. For example, the F1 measure. Before we introduce the F1 measure, you have to know what is precision and recall. And if we treat 1 as positive and 0 as negative, the definition of those 3 measurements are listed here. You can take a look. Let's move on to 3 popular tricks to deal with good dataset. We choose those 3 tricks because they are widely mentioned on the internet. We search about this problem, let's say on Stack Overflow or cross-validating and other websites, and there are many academic essays or many people actually on the internet. They are mentioning these 3 techniques, so we want to have a try. The first one, cost-sensitive logistic. What is cost-sensitive classification is basically it sets different weights to misclassification. Usually we think, okay, a mistake is a mistake. So false negative is the same as a false positive. But in this case, and actually in many other cases, it is not. So here, a false positive, which means predicting a wrong customer, is not that costly. But missing a potential customer, which means it's a false negative, is much more costly. So we assign different weights to these 2 values. And you can see the result of a cost-sensitive logistic regression is like this. The profit in this case is around $3,300, and the OVR is 31%. The definition of OVR is given here. We can see there's like remarkable improvement of the model. If you still remember, the original logistic regression only gives around like 50 prediction of ones, correct? And this one is giving like 165, so it's like 3 times the amount, which is really good. And for cost-sensitive support vector machines, we are having a problem. For some reason, the cost-sensitive SVM doesn't work on non-linear SVM. Regardless what kind of weights we set. You can see from the code here. We've tried different weights, but the model just always predicts everything as 0. We haven't found out the reason yet, but we'll keep investigating on this issue.
Okay, let's move on to the other 2 tricks. The second trick here is undersampling. So since our problem here is that we don't have the equal number of the data points labeled with 0s and 1s, so why not we just adjust that and make them equal? The idea is simple. So we can actually remove the extra data points labeled with 0s to make the number of data points labeled with 0s and equals the same. The disadvantage here is very obvious. So based on our available data points, the training set will be very small. So the model based on this training set is actually not so satisfying. The model is starting to predict 1s, but then it's not predicting 1s very frequently. So we actually have negative profit here. Based on some similar ideologies, we can also add more data points labeled with 1s and using the SMOT method. What is SMOT? SMOT method is used to generate stimulated points around the original data points. And as we can see from this graph, at first, the original data set, in the original data set, we don't have the equal number of orange and blue data points here. After applying the SMOT method, we automatically generate blue points so that now their numbers are equal. The SMOT methodology is also included in the Python package. Let's take a look. Yeah, it's here. So we use the package called imbalanced learning, and then we can generate the smooth result using this code. You can have a look. However, based on this ideology and applying those two methods, by the way, the add same method is just an extension of the smooth methodology. The basic idea is the same, but the prediction results are still far from satisfying because the models are still not predicting enough number of ones. So what should we do? We decide to have a combination of the two oversampling and the undersampling method. After applied those two methods onto the logistic regression, we see that there's a huge improvement. You can see the specific statistics here. But what happened? So what we have done here is that since both the oversampling and undersampling has their advantages, so we just combined those two methods together. So we still reduce the number of zeros, but we keep 1/3 of zero data instead of the originally what we done in the previous example. We only keep 1/9 of the data, and after keep the zero data, we use mode to stimulate data points labeled with ones, so that now those two kind of data points are numbered the same. And then the prediction result is pretty amazing. We see that the model is starting to predict ones, and the overall profit in this case is very high. And let's see from the OVR, which we can recall the OVR defined by the profit divided by maximum the maximum possible profit, so that we can see that the OVR of 81.94% means that we almost get all the possible profits technically available. So this is a very good result. So let's move on to our conclusion part. After finishing all those research, we can draw 4 conclusions. First of all, the accuracy of the model is useless when dealing with skewed dataset, and instead we should look at precision, recall, and FF measure. And second, the popular tricks used have been improved to be effective, but they are not the panacea. We should actually try different ways before we get a good result. And actually, we can also try to combine those several different ways. And then the SVM model shows this quality, which is not surprising because it provides decision boundary that is nonlinear with kernel. And at the same time, logistic regression is a generalized linear model, and it's almost impossible for real-life data to be linear separable. Thus, it performs worse than SVM models. Okay, thank you for your attention. Alt+F